This presentation serves as a demonstration of an application created by the engineering health team for the purpose of multi-camera calibration using a checkerboard with known cell dimensions. In this presentation, we employed 6 different mobile phone cameras, each with varying frame sizes and frame rates, although the method can accommodate any number of cameras. To begin, the initial step is to either create a new project or browse an existing one. Subsequently, videos that have been previously synchronized using third-party software must be copied into the project's designated videos folder. The second tab of the application provides an option to synchronize the frame rates of the videos. Following this, the videos need to be discretized into individual frames. For example, setting the step value to 30 for a 30 frames per second video will capture 1 frame per second, while setting the step to 15 will result in 2 frames captured per second. It's essential to note that, as a general guideline, approximately 20 to 25 images are required for each camera to facilitate camera calibration. The subsequent step is designed to ensure that all discretized images from the various cameras are of the same size. Then, we need to enter the specifications of the checkerboard. In the Monocular Calibration tab, we begin by selecting the folder containing the discretized frames from all cameras. The application takes an automated approach to eliminate frames where the checkerboard is either absent from the scene or obscured and where an insufficient number of cells is visible. Furthermore, it prompts the user to verify the accurate detection of checkerboard corners and then save that image for use in subsequent monocular camera calibration. Upon loading the images from each camera, the application proceeds to calculate intrinsic camera parameters, including focal lengths, principal coordinates, and lens distortion coefficients. The subsequent step involves identifying matched images from the user-selected pairs of cameras within the previously verified repository. These matched image pairs are saved for use in stereo camera calibration. If there are checkerboard images visible to all cameras, the application also stores them to validate the multi-camera calibration. Moving to the next tab, we delve into stereo calibration, also referred to as dual camera calibration. Using the Monocular calibration file and specifying the camera pair we intend to calibrate, the application allows us to compute the extrinsic camera parameters, determining the spatial positioning and orientation of the cameras. This process needs to be repeated for the camera pairs we wish to employ. In the next tab, we want to perform the direct linear transform, DLT process, and derive the projection matrices. Before embarking on this calculation, we extract the coordinates of the checkerboard cell intersections as the image points. These image points are used to determine the 3-dimensional object point coordinates. To extract these coordinates, we navigate to the corresponding folder containing images from the paired cameras. The extracted coordinates are then saved as an Excel file and will be loaded when initiating the DLT process. The subsequent phase involves computing the projection matrices, the results of which will be utilized later in our developed 3-dimensional pose estimation application. This image depicts the AI-based markerless 3-dimensional pose estimation algorithm developed by our team. To calculate the projection matrices for the stereo camera system, we must first identify the specific camera pair we intend to use and decide which one will serve as the reference camera. Following this, we load their intrinsic and extrinsic parameters and initiate the projection matrix creation by clicking the appropriate button. This process should be repeated for each camera pair we intend to employ. The subsequent subtab is dedicated to triangulation, or the three-dimensional reconstruction of the checkerboard cell corners. The image points, or the checkerboard cell corners, extracted from both camera views in the previous step, along with the projection matrices of both cameras, will be imported into the application. Through the use of the direct linear transform method, the three-dimensional coordinates of the cell's corners will be determined in space. The images display the image points as blue dots in both camera views, while the three-dimensional plot shows the reconstructed coordinates of the checkerboard cell corners. Furthermore, the application calculates the root mean square error of the reconstruction, which, in this case, is measured at 0.47 millimeters. In the next tab, the application provides the option to visualize the reconstruction results from different pairs of cameras. The final tab is designed specifically for multi-camera calibration. As mentioned before, if we have common images between all of the cameras in our scenario, all 6 cameras, the initial step involves extracting the checkerboard cell corners or image points from all camera views. If we do not have this commonality, we can proceed to the next menu. In this process, we first load the Monocular calibration file containing intrinsic camera parameters. Subsequently, we load the extrinsic camera parameters for each pair of cameras, which are the translation and rotation parameters for the second camera with respect to the first one. For example, the second camera to the first camera, the third camera to the second camera, and so on until we reach the sixth camera to the fifth one. Through matrix transformations, we determine the spatial positions of all cameras concerning one another, considering the first camera as the reference. This step leads to the calculation of projection matrices for the multi-camera system. The scene layout menu visually represents the camera layout within the space. In the final stage of the multi-camera calibration process, for a better visual understanding of the calibration procedure, we load the corner coordinates extracted from the checkerboard cells in all camera views and the calculated projection matrices. This enables us to compute and visualize the three-dimensional coordinates of the reconstructed points